Hi everyone, welcome to our presentation on the A-star pathfinding algorithm. My name is Mohammed Lukman, and today, along with Karan, we are going to walk you through one of the most important algorithms used in AI, robotics, and game development. And what makes today's session special is that we are not going to talk about A-star. We are going to see it think. We have built a live visualizer right here that shows every single decision the algorithm makes step by step in real time. So let's dive in. So imagine you have a grid like the one on the screen right now. You have a starting point and an ending point, a bunch of walls scattered between them. The question is simple. What is the shortest path from start to end? Sounds easy, right? But think about it at scale. GPS navigation, enemy AI in video games, warehouse robots, they all face the exact problem. On grids with thousands of cells, brute force won't cut it. You need something smarter. So that's where A star comes in. A star works by scoring every node it considers using one simple formula, which is f of n is equal to g of n plus h of n. Let's break through it, where g of n shows in green is the actual cost to reach the node from the start. Every step taken adds to the g of n. Okay, and then h of n shows in yellow. It's heuristic, an estimate of how far we still have to go to reach the goal. Okay, and f of n, which is shown in purple when we run at full speed. Okay, it is the total priority score. A star always picks the node with the lowest next. Okay, and the genius of A star is that it doesn't explode blindly in all directions like other algorithms. The heuristics guide towards the goal, saving enormous amount of time. We use Manhattan distance as the heuristics. How do we calculate h of n? Why do we use Manhattan distance? You can see in the image that we have Euclidean Manhattan distances. Okay, we can't actually travel diagonally in the grid, so we we can't use Euclidean distance here. So we are choosing our Manhattan distance, which is a simple mathematical formula. Okay, it's h of n is equal to modulus of x goal minus x n plus modulus of y goal minus yn. Okay. On the labeled grid, you can see the column number 0 to 19 on the top and the row number 0 to 9 on the left side. Manhattan distance simply counts how many steps to the right or the left plus how many steps up to the down. You need to reach the goal if there were no walls at all. Okay, this is called Manhattan distance because it mimicates the navigating city blocks in Manhattan. Okay, in New York, and it doesn't go diagonal. You can only move up, down, left, and right. And crucially, it never overestimates the real distance, which is what makes it an admissible heuristic. And that's why A star is guaranteed to find the shortest path when using it. Okay. Now Karan will show us the live demo.
Now let us look at this example over here. So here is a 20 cross 10 grid initialized at the 0th index. Let us start the initial search, which is not the final search. So first step, we are at 2 cross 2 comma 2 node. Then final node is at 7 comma 70. So the heuristic function is 21. So we have to reduce this. So first it obviously tries the above step or it tries the left, and then it goes towards the right to 1 comma 3 being the least heuristic functions, as you can see here, which is a total of 22. Then it goes towards the right again by comparing the other nodes, and this happens until an obstacle is blocking the path, so it takes The next immediate other option, which is the heuristic function, is at 21. It has tried all these other combinations. Then it goes here. Then it travels towards the heuristic function's goal, which is the end part within these steps. And as you can see, g of n is at 6. So we have taken 6 steps. And we are reducing the h of n as we progress. And when this happens, it is visiting all the other possible paths until it encounters another node. But over here, the obvious answer is it goes down as is the only final end. And then an path is established. Now it backtracks to the goal. As we can see here, it backtracks to the source, to the goal, and then it initializes each and every path to the most optimized route. As the end path is reached, the search is complete. Now let us look at this application. Over here, these are the obstacles. Now there's a building where the truck is static. Now it has to come towards the end goal over here. So let us look at a slow search, how it establishes the route. So it goes first in this way and then reaches here at the end part. Let us look at another example. In this, we have to cross the river and go towards the end goal. These are the obstacles of the river, assuming there's a bridge here. So the heuristic function is at 24. We have to minimize this and go towards the end goal. Let us take the step 1, which is 8, 2. So it takes the step forward towards 8, 2, and these are the explode nodes 9, 3 and 9, 1. 9, 3 could have been an option, but this being the most efficient, it goes here. Next 7, 2, and this happens until a dead point is reached and it takes a right. And next, this is the most optimized path to the goal, as we can see here towards the heuristic function. Since there's an obstacle in between, it backtracks and tries other nodes. This happens until a clear opening is found. Over here, there's an opening, and then immediately it goes towards the end goal. And now an optimized path has been found. By backtracking, it takes the optimized path towards the end goal.
Yeah, this is a summary. And to summarize, A star uses f of n and g of n plus s of n to parallelize the most promising nodes with Manhattan distance as the heuristics on the grid. It effectively finds the shortest path, never revisits the node, and always gives the optimal answer. We build the visualizer to make the process transparent. Every step, every score, and every decision is explained in real time. We hope this demonstration made ASAR feel intuitive rather than confusing anything. What do you say? And thank you for watching, and feel free to try the visualizer yourself. Draw on your walls, change the speed, and watch it start. Thank you.